embedded in a large program for the neutrino physics, as I just said, which is called DUNE. And this is why I'm using this logo at the beginning of this presentation, because in particular ProtoDune, but also Lariat, are two experiments that one is taking data, the other one is in the design, final design phase, on the same line of physics, to support the development of the overall neutrino program in the US. In particular, these two detectors, Lariat and ProtoDune, are focused on the study of hadron interaction using the liquid argon TPC technology. That is the one that has been chosen for the entire neutrino program. And in the study of the hadron interaction in liquid argon TPC, with the argon as a target nuclei for the hadron interaction, is an important ingredient to know and to better reconstruct the neutrino interactions where hadrons are possibly created by these interactions. So we study hadron interaction specifically in the same energy range and with the same type of particles that are generated by neutrino interactions for the future neutrino program. And this is the connection between this effort and the overall effort of the neutrino program. Okay, this was sort of the introductory introduction for this presentation. And here I want to maybe enlarge a little bit the discussion on what is the neutrino program, inside which, as I said, the two experiments that I'm going to talk about are embedded. So we have essentially approved since a couple of years a very large program which is born as to be a worldwide international, global international program requiring, requesting and inviting to participation all possible fraction of the entire worldwide community, because the effort that is going to be produced and necessary for this program is so large and so endeavoring that only with the support of the entire worldwide community that will be made possible. The size of this experiment, of this program, is similar, if not even larger than the effort required to set up the two large experiments at CERN, which are the LHC experiment, ATLAS and CMS. So we are talking now about this program, of a program which has the size, in terms of collaboration, size of collaboration in the order of 1,000 people, and in terms of financial support, and even more of the technological effort that will be required, which will be comparable, if not higher, than what was required to set up the two largest experiments ever built in physics and particle physics in particular. So this is the current view of the entire research field in particle physics, but even broader than particle physics. There are some boxes here which indicate what are the main line of development of the current research, going from exploration of the nature of dark matter, understanding what is the nature and the origin of the dark energy which we have sign off, but also exploring deeper and deeper the standard model, looking for new particle and new type of interactions through the LHC experiment, and going through an advancement in the search along the physics of neutrinos toward this final conclusive elucidation of the question related to the neutrino mass and related oscillations. This is also supported, the entire program has to be supported by the continuous development of new tools to carry on these projects distributed along these various lines of development. Well, the worldwide neutrino program essentially represents itself in this box, coincides with this box. but not necessarily only this one, because it includes also the development of the specific tools to reach this program or to make this program possible, and also covers partially this box here with the search of new particles and possibly new interaction through possibly a portion of this program that involves the short baseline neutrino experiment at Fermilab, looking for possible sign of existence of the additional neutrinos, which are commonly indicated as sterile neutrinos, whose hints have been maybe somehow proposed or found of their existence in a previous experiment by the end of the 90s, beginning of the 2000s. So this is the plan. The worldwide neutrino program then is meant to be a world-class facility based in the US, but composed by a worldwide community for a long baseline neutrino program on a long baseline base with accelerated neutrinos, and the same detector also cover additional topics of research, since it's going to be located underground and therefore opening the possibility to investigation on astroparticle physics, like supernova detection, neutrino detection, as well as atmospheric neutrinos and solar neutrinos, and possibly rare phenomena like proton decay. And at the same time, this program also, as I said, is composed by a suite of experiments composing the short baseline neutrino program at Fermilab to cover or to explore the possibility of new phenomena and new particles. Let me then say June is the long baseline neutrino program. Is meant to have composed by a beam of neutrino, a high intensity beam, the highest ever reached intensity beam of neutrinos generated at Fermilab with a dedicated new neutrino beam line that send neutrinos from Fermilab in near Chicago towards South Dakota, where in a deep mine underground there will be located a large liquid argon TPC experiment over a distance of about 1,300 kilometers of distance. This is the plan for the installation of, This is the plan for the installation at Fermilab of the new neutrino beam facility, sending this beam again to South Dakota. This is the building for the mine, and now it's not anymore used as a mine, but that will be renewed and to host the large detector that makes these two experiments. The short baseline program, that is the other part of this program that I mentioned now, is instead made at CERN, at Fermilab, with a suite of 3 experiments along an existing, now running beam line, which will send neutrino beam through 3 detectors positioned at 3 different locations and distances from the source, and therefore exploring the possible pattern of oscillation for this still unknown and assumed to be existing sterile neutrino, whose existence has been essentially inferred by an experiment that has never been demonstrated to be wrong so far, even though several attempts have been done in the past. And this experiment should clarify, is meant to clarify this issue or this question, either confirming or discounting the hypothesis of sterile neutrinos at a very high level of confidence. So the liquid argon TPC technology, and I will say a few more words about that, is the technology that has been chosen for both the short baseline neutrino program for all the 3 detectors on the short baseline line, and as well for the very large detector in the far location on the long baseline neutrino beam line. Just to, I did not mention that explicitly, but These detectors located far away need to be very large to be sensitive to the flux that is sent at a distance of 30,000 kilometers. And the size of this experiment is absolutely, astonishing, because it consists of 75,000 tons of liquid argon. And 70,000 tons of liquid argon is an amount that is a good fraction of the whole existing argon in the atmosphere. And it consists of a detector that is, in the range of hundreds meters of length times tens of meters of height and depth. So it's divided in 4 segments, but I mean the total amount is absolutely incredible as a project to be realized. The short baseline detector, at least that's smaller in scale, are only in the range of 1 kiloton, while the other one are in the range of 75 kiloton, as I said. But the main question is why liquid argon type projection chamber has been chosen for the entire suite of experiments of these very ambitious neutrino projects. Because essentially, this is the best technology that has been developed so far for neutrino physics. It can cover from very low energy neutrino energy up to relatively high energy with constant efficiency. From the few MeV scale to the picture, here is the vertex of the invisible neutrino that interact with the material of with the proton of the hydrogen content of this bubble chamber and produce a long muon track. So a neutrino mu converts into a charged lepton muon that escapes there, and then also a proton with a short track here, and the pi with a somehow longer track, the pi meson that is indicated here. Amazingly, with the argon detector that I will talk about in a minute, more recently, an event very similar to this one has been detected, with a neutrino coming from this side, producing a vertex with a proton, with a long muon that escaped the detector, and with a charged pi here. So they look exactly similar with each other. With the additional advantage of this technology, not only to show how the event looks like, how the event is developing into the argon, but also giving you, in terms of, the scale color here is not random. It tells us something. It corresponds to the density of the energy deposited along the track. And if you sum segment by segment over the whole track, you can reconstruct the full energy deposited by this proton. And if you sum the energy deposited by this proton, by this muon, and by this pi, you have the energy of the incoming neutrino. And this is the great secret of the beauty of this technology, that allows you to see what happens and also to measure all the details, the fine details of what is happened, and thus reconstructing the properties, energy and type of the incoming neutrino. Okay, so here is just a cartoon to illustrate how the liquid argon TPC technology works. This is an event that is generated inside a volume of argon, constrained by an electric field. At one side there is a cathode, and the other side there is a series of planes of wires. And the use of, as an anode in this ionization chamber, of wires and a consecutive number of planes of wires is shown by this cartoon here. So each of these wires here is read out through an amplifier, and if recorded, provide the development in time of the signal that is recorded. If you put together the signal recorded by all the wires in one plane and all the wires in another plane, you have essentially two images of the two events. The two images, semi-independent images of the same event. And if you combine the information of these two images, you may, which are 2D images, each of the two, with one coordinate in common between the two, you can reconstruct the full 3D topology of the event. And this is what we obtain. This is the image of a 2D image of this event, which actually is a real event. It's not only a cartoon. Well, now, I mean, before arriving to this level, of course, I mean, there was, so this is the principle of functioning of this detector, but the important message here is that it took a long time to reach, that was required for this technology to become available for an actual detector, for an actual experiment. It required about 25 maybe years of development. So, it took us a long time to develop this technology, and in particular, this technology has been developed under, the R&D program of the Inverno collaboration that developed that program, this program in Italy and at CERN, starting from the early 90s and across the whole period from the 90s to the beginning of this century. And which led finally, I never use this again, and finally this program led to the realization of the first large volume detector that has been running and taking data for 3 years at the Cavanna laboratory, and is now being refurbished to be sent to Fermilab to take part of this short baseline program that I mentioned before. So Inverno has been already taking data for 3 years, is now going to move to Fermilab in early 2018 or end 2017 for another set of run together with the other 2 detectors that I mentioned before on the short baseline retrieval. For making this short baseline program here as a part of the worldwide retrieval program. So with 3 detectors. This one, microgroup, is already existing, is the one that I mentioned before, exists, takes data today, and it is running since sometime last year. And another third detector is the SPAT, the short baseline retrieval detector, that is under construction and will be positioned nearby the source for the suite of the 3 experiments for the short baseline. But Inverno also somehow generated, the development along Dune, along another line, the longest line way of development. And at Fermilab, it has been created and run a relatively large volume detector, 35-ton active detector here, which is the prototype for another large detector, which is called Proto-Dune, which is part of what I want to discuss more into detail today, which is, the necessary large-scale, 1 kiloton scale. This is half a kiloton detector. This would be 1 kiloton detector, which would be just, the pilot experiment for the large Dune experiment, whose is not in scale. This is the 20 kiloton one module, and then there are other 3 not shown in the picture for the final Dune experiment. This also comes from the same, however, was not, the origin of all the old story is from Inverno, but there was also independent and semi-independent development at Fermilab. One with a smaller prototype that was run between 2010 and 2011, that based on which that was essentially built. And also another line of development, starting for a tabletop experiment called Argonaut, which I show here, implementing the same technology on a small scale, which ran over, however small, but was running on a neutrino beam first in 2009 and 10, and opened the way the collection of neutrino events with the liquid argon TPC. And there is a strong connection between the development of this detector and this one. But this detector also has been, after being dismantled from the NUMI beam line at Fermilab, became now the Lariat experiment with sound amplification, which is the other experiment that I want to talk about today. So today I will now concentrate on prototype, but first on Lariat. And so I made all this discussion just to give you the full picture. All this, is essentially part of the large neutrino program. This is what Argonaut showed, and is the starting point of the whole program in the US. Having a picture of this way, where you see neutrino, well, you don't see, but you see the vertex where neutrino interacted and generated. This track has been associated with the pion, this other track with the muon, this other track with the proton, and these four small showering particles are products of pi zero emitted at the vertex, decaying to pi zero, decaying into each one in a gamma-gamma pair, and each gamma producing a shower. So 1, 2, 3, 4. So the complexity of this event with 3 pions, 2 neutral pions, 1 charged pion, 1 muon, and 1 proton, distinguishable and reconstructible in all detail, and calorimetric detail as well, as this image shows, is the convincing element that led to the choice of the liquid argon technology for the entire program. Now, what we need now, we need to, the idea is to, as I said, in a neutrino interaction, you may produce hadrons, proton, pi, charged pions, neutral pions. So what we, and possibly even chaos, more rarely but chaos as well. So we produce, neutrino can produce, in the energy relevant for this program, hadrons, protons, chaos, and pions. The idea then is to develop a system to collect pions, protons, and chaos in a sufficient large amount of sample in order to develop all the needed tools for reconstruct them as carefully as possible using this technology. And then after this will be developed in full detail, this reconstruction capability will be plugged into the reconstruction capability of the neutrino, of the detector for neutrino physics. So the goal, study in liquid argon TPC particle emerging from neutrino interaction, is the study, this is the goal of the program, study in liquid argon TPC particle emerging from neutrino interaction for both the short and long design neutrino, relies or will rely, or is going to rely on the study in the same liquid argon TPC of particle emerging from a beam line that provides charged particle, while this beam line is tuned to provide to this particle the same energy range as produced by the neutrinos. And this is the spectrum of the various particles that are produced by neutrino interaction for the long design program. Here you see muons, electrons, pions, kaons, and protons shown here. They're all in the range essentially below 1 GeV with a log tail attack energy. And so the idea is to create low energy, this energy, beams of charged particles and shoot these beams into the liquid argon TPC and collect this data. And studying this data will be a driving way, a driving tool for the reconstruction of the neutrino events later on. And it was not easy to design a beam line capable to cover this energy, but this is what has been realized for the Lariat test beam line, and it's the same thing that is going to be realized also for the next generation of this kind of effort. So I mentioned pions. We have intrinsically interest in studying pions, but the important thing is because they are produced in neutrino interaction. And in particular, I want to mention the following. The major difficulty right now is to take into account the nuclear matter that somehow is between the genuine neutrino interaction and what we see in the detector. So nuclear matter is where protons and hadrons are living, and so if a neutrino interacts inside the nucleus, before the products emerge outside of the nucleus, they may re-interact and appearing differently compared to what they were generated. And we have to take that into account. And this is also part of this study. Studying the effect of the nuclear matter along the development of the event in the detector. So I'm not going to mention to spend time on this because I want to go faster on some more relevant things to say, but essentially we know how pion interact in matter. However, this is a plot of the cross-section of pions subdivided in various subchannels. The total is here, and the other subchannels whose sum provide this total cross-section as a function of A, the mass of the atomic or nuclear target. And for argon, which is A equal 40, there are essentially no measurements available. While there are for other lighter or heavier elements, in between and around 40, there are no measurements. So this also is one of the main motivations to have direct measurement of some quantities which have never been measured so far. And this is what Lariat succeeded to measure recently. Just 2 months ago, the first result appeared, and the run is not over. I mean, it's going to end tomorrow, the second run of Lariat. But this is just the beginning of the story. So these 2 runs of Lariat are the premise for another set of measurements that will be carried on with a much larger and much more performing detector, which will be prototyped to be built at CERN. And this will extend the measurements where Lariat, which is a tabletop experiment, cannot go. Similarly, I would say there is a large interest in collecting kaons and studying the interaction of kaons in the target material in argon. These are totally unexplored field or type of interactions, and these are very relevant because of the study of the nuclear decay, whose favored by some theoretical prejudice can go through decay into antineutrino and kaon. So it will be extremely important to collect data with kaon. Actually, we already have a decent sample of this. Okay, so let me go quickly into first Lariat. Lariat is, this is a picture of taken while it was snowing 2 years ago in the beginning of the first run in the Mason building at Fermilab, where charged particle beams are generated, and we use this charged particle beam to generate a tertiary beam of low energy pions and kaons. This is a picture of the test of the accelerator complex at Fermilab. There is this beam line here that moves protons up to a target, and which are coming here along these lines, and then this is now coming from above here. I mean, this has to be rotated upside down to be compatible with this picture, but in any case, the pion beam, this red line, comes this way, enters this large building, and Lariat is located in this part of the building. We had to make and set up a beam line to move from a pion beam of high energy into a low energy, below 1 GeV beam of particles. This required a lot of effort also in setting up a number of detectors along the beam line, to make it. So the target is here, and then there is a collimators, wire chambers, time of flight, and the dipole magnet that bend the particle and give momentum measurement, essentially, momentum sensitivity to momentum. And this is the TPC, the liquid argon TPC sitting at the end of the line. Okay, so in 2014, the beamline was essentially assembled in this area with all the elements, and colleagues working hard in putting this together. This is the beamline when it was almost completed, with the two magnets here that provide momentum spread for the particles. And then we started measuring what the beamline provides, and we found that we have pions, protons, and in between the two there is a fraction of these events which are chaos. And then that can be distinguished though from our beamline. And this is what we can see in a better way. So combining information from the wire chambers that provide momentum measurement and the time of flight that provide particle identification, we have these three very well separated blobs. This one is where pion and the remaining contamination of muon and electrons are concentrated. This is where protons are produced. And what is in between here is the minor but not negligible sample of chaos. The setup of the detector took place quite quickly and efficiently. You see this object here is the cryostat hosting the TPC, which is this box with wire on one side and the cathode on the other side. You remember maybe this cartoon that I showed at the beginning. So this is the real object, which is something that's a meter and a half and 80 centimeter tall, 60 centimeter thick, and so on. So it's essentially an object that stays on this table, if you want. Only that on that table. And then electronics was installed in it, tested. The photon detection system was also installed. Liquid argon provides also is a very efficient scintillator, so we collect also scintillation light and not only charge readout. This is how some pieces have been put together. This is how the photon detection system look like, with some photomultipliers, some silicon PMs, and here are the first signal that we detected from a silicon PM and from the photomultipliers. As I said, this is cold electronics. Cold electronics is the future of the electronic readout for this type of TPCs. All is in cold, so electronics like to live in a cold environment to reduce noise, but we need to make it carefully, because once it's inside, you can never access this anymore, so you have to be careful and making things correctly. And this is what was done, and this electronic performs amazingly well, with the signal to noise that reach in run 1 the value of 50, and run 2 the level of 70. Take into account that in the previous runs of the similar, the other pre-existing liquid argon TPC, the signal to noise was in the range of 15, while here we have 50, and the current run that is still running today is at the level of 70. So you see, this is one signal seen by a wire, where this is the noise and this is the peak generated by a minimal energy particle. So the development of this technology is becoming more and more advanced. Okay. So it was amazing when the detector was put together and closed, and the cryostat was filled up with argon. That ended on April 30, 2015, and then we switched on a voltage on the cathode, and then we started up the acquisition system, and 3 seconds after, the first images came out. A little noise here, but that's it. So, working immediately at the best level possible, almost at the best level possible. So we had the first run, and then the second run, which ends on August 1st. But actually the beam will be closed tomorrow night. So we are in the last day of a 5 months long, 6 months long effort, which was not easy to take over, but we had a lot of help, and we made that. Okay, this is something that I already mentioned. The science that we want to perform is hadron interaction studies, pion and chaos, essentially, and then plus another number of things. Pions can do a lot of things. There are a lot of type of interaction. This is, interaction for people maybe not as young as most of you. Remind, all kind of physics with delta excitation, decay, and detection of all the various type of interaction that pion can perform. But these have never been tested and checked and studied in our work, and this is an important step to fill. So here, for instance, we have inelastic scatter, elastic scatter, where essentially the pion just make a kink, or inelastic, where you may, through a delta excitation, provide a pion in final state plus a kicked off from the nucleon, or can be absorbed with no pion in final state, but just a number of nucleons, or can exchange charge. So a charge pion can flip through a delta into a pi naught, and other type of interaction. Now, these are real events collected by light, real events at the highest possible level of performance of the detector. So you see here a pion entering, making a kink. This is an elastic scatter that you can recognize by eye. This is an absorption where you enter a pion and this makes 3 protons. The red color here is an indication that the high ionization density, which is typical for a proton, and then you can run your reconstruction algorithm and this will tell you that this is a proton, all of these. You can have multiple hadronic interaction with a pion that here emits a proton, continues as a charged pion, and then make another interaction with some more prongs produced. Or can be finally a charge exchange. This is a beautiful event with a charged pion that interact here, produce a proton, and the pi naught would decay into a gamma-gamma pair, and each gamma produces a little electromagnetic shower that is visible here. Or can be even a more energetic event with pi naught, pi plus, pi minus event particle generated at the interaction products. And these are real events, and you can, looking into it, you may understand which type of interaction that is. I think that no other experiment ever looked into this kind of physics with this type of access to the information. Kaon as well are very interesting. They can do a lot of things. In particular, K- can produce interaction with strange conservation that results in emission of baryons with strange content in it, which in turn may decay further on by weak decays. So the chaos sector is also very interesting because it is essentially unexplored with this type of technology, and whose result can be even more astonishing than the one that I showed you before with the pions. This is an event that was collected during round 1. So there is a pion here. You recognize here 2 shower which are pointing to the vertex, so this is a pi naught decay, and then there's a pion that stops here and decay into a muon and electron. Well, years before, when we were studying designing the detector, we were running simulation to see what a cam can look like. And we had a collection of events generated by simulation. And when we saw this event, somebody recalled that simulation. So it is amazingly identical. But this is a real event. This is just, a software process. but it is so clean, so precisely measured or visualized that you don't need to go much further to be convinced of what that thing is. And this was from 3 years before we collected this data. We have a number of beautiful Kaon candidates now, with a lot of, for instance, here is a detached vertex, and a pi naught also shown here. This also is a very beautiful event with a pi naught. Presumably is a lambda zero or a sigma zero that travels and makes a decay into pi and proton here with a detached vertex. And this is a Kaon decay at rest, with a Kaon that decays slowly, that stops slowly at the end. You see the increase of the energy deposited toward the end, which means that the particle is gradually slowing down in argon up to stop, and then decays into a muon and then an electron. Okay, so these are beautiful events, all of them, but one can ask, did you make any measurement out of it? Actual physics measurement, physics quantity? And the answer is yes. That is what has been done in the last few months with a very big effort from a number of people of the Larry collaboration. I'm not sure I want to go too much into the detail how we made it. However, just let me say that we essentially reinvented a technology, a technique, an analysis technique to make measurement of the total pion cross-section, which is this quantity here, which is connected to the probability of a particle to survive crossing a layer of material of thickness Z. Okay? So this is the probability of survival of a particle traversing a quantity, a thickness of material Z, of what material? The material of density N, when the cross-section of interaction is this quantity here that we want to measure. Now, the probability of interaction is essentially can be represented by the ratio of the number of interactions. So the probability of interaction is 1 minus the probability of survival. It's just a complement to 1. And the probability of interaction is the ratio can be approximated by a measurable quantity, which is the number of interacting particles across the same layer of material over the number of incident particles. And this ratio, it gives a measurable quantity. That is an approximation of this quantity, of this ideal quantity, which is connected to the cross-section by this formula. And this gives us the way to measure it. If we have this layer, the thickness of the layer reduced, we can expand the formula before, and then we have this relation, which if you invert this, you ended up with this quantity here. So the cross-section is 1 over nz, which is a quantity that we established, we define experimentally, and this is what we measure. Now, our target, however, our device, is not a thin target, so this approximation cannot be valid. But the question is that with the granularity of the readout of this TPC, which are made by the wires, we can subdivide this TPC even, well, in the analysis, we can subdivide this volume in slices, thin slices, and therefore making this approximation valid. And this is a feature of the technology, to have the wire planes at a distance of a few millimeters with each other. A few millimeters is sufficiently low to allow us to use this expansion and to use this formula to calculate the cross-section. So now, the question is that we have to measure for each pion that we produce and send through our TPC, how many of those interact over how many we send on. So, follow me for a second on this cartoon. So we have here a pion that enters the TPC, propagates through the TPC, at some point interact. So the interaction happens here, but all over this place here, It doesn't interact. So it traverses all possible layers without interacting. And therefore, these are just corresponding to the incident counting. So we created 2 histograms. At the first layer, it doesn't interact, but is incident. So we fill this histogram with 1 entry and no entry in this histogram. Then we go. Then we perform the same thing all over the track, layer by layer. Okay? All over here, we don't interact, there is no interaction, but is incident. So we continue filling this bottom in the histogram, and nothing is here, until you reach this point. And at this point, it makes an interaction. And therefore, we count these in this bin, in this histogram, and in this histogram again. I did not mention that explicitly, but we know the energy of the particle that comes in. In each layer, we account for the energy that is released in the previous bin, or the previous layer. So we know layer by layer what is the energy, and we fill the corresponding entry in the corresponding histogram at the right place in terms of energy of the pile. Okay? This is the secret of this measurement. This has been done for many piles, all the piles that we collected, and we filled up, the 2 histograms. These are currently actually the real histogram that we obtain for the analysis of the data, and then we take the ratio bin by bin of these 2 histograms, and we make the measurement of the cross section. And this is represented by the black dots, while the blue ones are what we expect from Monte Carlo simulation. And here is the measurement. This is something that has been, it looks like simple. Indeed, reconstructing this was not as simple as I said. It requires several months of scratching head and fighting with a lot of difficult things to remove, background, selection of the event, and in developing this technique for this analysis. And then we showed that in a public conference, and well, that made quite a bit of a splash at the moment. This is the collaboration, and I reserve that to the end, but one of the main reasons we succeed in doing so, and also to keep our detector alive for all these second long and exhausting 6 months of 24/7 shift, are also largely on the help and the support and the skill of the people that I show here. Some of those are here, and I have to thank them for this contribution. Okay, so this is what Larry did and why Larry did this measurement. Now let me switch. How much time? Okay, I think I will be even faster. Okay. So let me switch now to Protodune. Protodune is the big brother of Lariat. Lariat is half a ton of argon. Protodune is 1 kiloton, so 1,000 tons, so it's 2,000 times bigger than Lariat. It will be built and at CERN and exposed to a beam which covers the same energy range but extend the energy range even at higher energies, moving from the 1 GeV up to, say, 7, 10 GeV. And that will be, this effort then with Protodune will be, recovering once again the same type of physics that has been developed with Lariat, with the same type of events and following analysis, but extending the range. Maybe I can go back here. You see, this measurement is statistically, good until, say, less than 1 GeV. We have data from round 2, which will be, which will allow us to, reduce the statistical error even in the range up to 1 GeV. But above 1 GeV, we don't have sensitivity, essentially, because the beam doesn't produce particles at these energies. Protodune instead, the beam at CERN for Protodune will be capable to extend their energy range above and up to maybe 10 GeV. And on top of it, for 1 GeV particle, the Laria detector is too small to contain them. And so in most cases, or in a good fraction of the cases, particle goes through and escape from the far end of the detector. While with the detector, which is 2,000 times larger, there is no issue of this, even moving up to higher energies. So that will be a very much complementary type of measurement done with a different beam and with a different detector, but implying the same technology. And this is what Protodune will be. So you see here the beam line that is under design at the moment, shooting particles, hadrons, therefore kaons, pions, kaons, and protons, toward a large detector, which is sitting down here, that I will show you better in the next slide. This is a top view of the installation. Actually, Protodune, you see here, Protodune replied twice. There is a Protodune dual phase and Protodune single phase. I will mainly concentrate on this, which uses the standard technology of the liquid argon TPC, but there is also another equivalently large detector that will be built, implying or using a variation of the same technology that I described before, which doesn't use the wires, but uses a different method to extract the ionization charge. So indeed, I mean, even though I will always say Protodune, indeed I'm talking about two Protodunes. And this is 1 kiloton detector here and one other kiloton detector here. So there are two gigantic detectors, twice as big as the largest detector ever built so far in this technology, which will be created, realized, and built at CERN. In this location here, which is at the end of the north area at CERN, where there are beams of particles, but this is a new extension of it to host these two detectors. All these parts from here to here are about 40-50 meters of a new platform, a so-called new platform, where these two detectors, completely new, this has been just made in the last few months. On March this year, you see here how that place looked like. You know, they were digging the ground to excavate the place for this platform. By end of March, I mean, the excavation was essentially completed. Then in April, they started to build the building around it. And a week ago, I took this picture of there, which is essentially the experimental area, the enclosure for the two experiments, one sitting here and the other one sitting here, is ready to go. And will be, delivered at the end of August, even before schedule. And then two beam lines will be in preparation, will be prepared, moving from here, pointing, out of this wall, which actually is being removed. When I was there taking this picture, they were removing this wall, and so having, the extension here connected with the rest of the area, which is beyond this wall. And so from there are beams that are arriving up to this wall here, and then they will be extended, and the beam lines will be created. This is another picture from the top of how the two detectors will be installed. Now, each of these, but let me talk about Protodune single phase, the one that implies the same technology that I described before. Looks like, the detector, the cryostat looks like this, will look like this. This is the cryogenic plant to extract liquid, purify it, cooling down and re-injecting the purified liquid inside the cryostat. Purity is an essential element of the functioning of this detector. But I need to draw your attention to the size of it. So it's 9 meters by 9 meters by 9 meters. And I don't know, 9 meters is, I think, a bit higher than this room. So it might be 1 meter or 2 higher than this room, in the peak of this room, and the size will be essentially the size of this. Okay, so you see, it will be a detector that will not sit inside this big room, but similar in size, but will not fit inside. So you can imagine how big or what the size of it will be. So this detector, but the story is not finished here, just for the size. It is the complexity of realize and build this detector inside this crater that is a very, very high challenge. This crater will be built leaving an opening, the so-called technical opening here, temporary construction opening. This is a door, I think 5 meters, 6 meters tall, but only 1 meter wide. And through this door, we have to enter all the components and build inside the detector, the detector itself. The goal of constructing this crystal is amazingly short. So the crystal will be ready by spring 2017. So we will start building before the end of this year, and in 6 months it will be built. This is what is anticipated, but that's what we will do. Then we have to insert inside the crystal. This is a picture of the inner crystal, the inner detector, the liquid argon TPC itself, sitting inside this crystal. And this is also a very large object, 7 meters, 6 meters, in component, in pieces. These are the frames for the wire planes. This is the cathode in between. And the other side, there are 3 objects of this side, of this type, also positioned on the other side. This is how it will look like during the installation, the area that I showed at the beginning in the pictures. Having the crystal, the opening. This is a clean room because the liquid argon need to be extremely pure, and all kind of dust or source of pollution that can enter the crystal can impair the detector once filled with argon. So there is a clean room, and you see here this rail that you see better in this picture. And so the component of the TPC will be appended to this rail, and while moving to this rail around into this loop, different components will be mounted on it. So these are the frame of the wire planes, electronics will be mounted, photon detection will be inserted in, and then coming to this large box where this object will be fully tested with the final data acquisition system. And then finally, from outside will be moved inside. And this is how one can see things happening from the inside. Okay, this is the man. So this is the man that asked for entering component, and then there will be these wire planes, 1, 2, 3 appended from the top, and then in a series of operations, the cathode will be put in between. Then the field shaping system, so the system that allows to have the electric field from the anode to the cathode uniform. There are panels of conductor will be installed one after the other. You see, in this cartoon, how one foresee to make it. And then there will be the other three planes mounted on the other side, and the same procedure will start, mounting the various components, one after the other, up to be here, when the detector will be completed. And hopefully, one can wonder where the poor man that was in there is going. Actually, there is a manhole on the top, on the roof of this crystal, where the man can go up and escape from there. The old mounting of this detector has to be ready by January 2018, which is barely 15 months from now. So I hope you can understand, the amount of work that is needed and how difficult it will be to maintain the schedule. But this is what we want to do, and this is what we will try to make. And why so? Because we want to make a physics run using the beamline that in the meantime will be accommodated along in this area from June to October 2018, because on October 2018 the beam will stop. And at CERN, the accelerator complex will be on a long shutdown period for 3 years. And this is why we're rushing as crazy to have this detector ready to take data before the shutdown happens, because otherwise we have to have three years to wait before having again the beam. So it's a great big run against the time that we have, which is very short. Okay, so I think this summarizes the main goals of what Protodune will make. It will be a first large-size detector where the TPC imaging will be aided by calorimetry in the high energy range. And this will help to maybe open the possibility to a new set of investigation that were never been exploited so far. However, with this detector can be explored. It will be, I believe, a fantastic occasion for having a lot of excellent PhD theses and publications. And the thesis that has to be done is essentially made here, exploring, in the higher energy range, a lot of mechanisms that with this TPC and with this type of detector will be available for exploration. Okay, I finished here. The time scale for Protodune is extremely short. However, Protodune at CERN will provide a possibility now, today, to have, for groups who participate to it, an in-depth experience with liquid argon detector from the point of view of the construction and operation, but also for remarkable physics achievement. I believe that this represented a very great opportunity, in particular for students and postdocs from university groups and young researchers, to create their background of skills and expertise, which will be what we need to have a new generation ready to carry on the investigation due in the next decade at the far side with neutrinos. Okay, thank you for the attention.
Questions? Just very fast. Are there some opportunities specific for Latin America in this program?
Absolutely yes. Absolutely yes. Actually, 3 months ago at Fermilab there was a dedicated workshop where representatives from Latin American countries have been called to participate and discuss and evaluate the possibility to be part of this program. The worldwide neutrino program is meant to be a worldwide program. Without the support of all the community from any country, it will not be possible to carry out that program. And that program goes through, as a first step, into the realization and run of Protodune. And, well, I believe that a number of Brazilian institutions are already, and Campinas in particular, are already part of Dune and also of Protodune. So some of the people from here are involved in this program, and once again I believe that opportunities for students and postdoc to participate in this program will be really extremely important for the experiment itself, but also for the growth of their experience in view, as I said, of future involvement in the big detector for neutrino physics. Not only Brazil, of course. I mean, we have been in contact, and we are in contact with several other countries, people from institutions from several other countries in the South America, and so I mean, it is a great opportunity because, you know, in some sense, we have in June the first, and in June in particular, the first ever combined participation of CERN out of CERN and Fermilab, you know, collaborating together for the realization of this experiment, representing in this way the first operational merging of the community in the US and the community in Europe, which is polarized by CERN, through CERN from many countries in Europe. What we absolutely want to improve and increase, and there is enormous space available for it, is to have a third pole added to these two, which is represented by Latin American countries. So it would be not only welcome, it would be necessary to have a strong support from Latin American countries. And I believe that Brazil may be the one that will lead that, I hope, and I'm sure it will be. Thank you, it's unexpected.